So let's see the third question. State Newton's third law of motion. In general words, Newton's third law of motion can be explained as every action has equal but opposite reaction. But when it comes to the statements, you must be very careful that you should write as clear as possible. So if, like, how do you write? So let me explain first and then write in the words. That will be easier. So let's say there is a there's an object on the table. So the object is the textbook. I assume the textbook, and then that's A, and the table is B, and then the A exerts force on B, which is equal to its weight, right? That's the weight. Every object exerts weight when it is placed on certain object. So the A is exerting weight on the B. At the same time, the B also exerting certain force, which is called normal reaction, on the object A. The forces are equal in magnitude but opposite in direction. That's what you need to explain. Okay, so if object A exerts force on on B, then object B also exerts same force, which means equal in magnitude. So same force means exerts equal force, you can write instead of same force, equal force, that is in magnitude, equal force in magnitude, and opposite force, which means in direction. Opposite means in direction on object A. So the object A exerts force on B. If object A exerts force on B, then object B also exerts equal in magnitude and opposite in direction on object A. That's the Newton's third law of motion. Let's see the 3b. A block X of mass mx slides in a straight line along a horizontal frictionless surface as shown in figure 3.1. This is the object X and this is the object Y. So the mass of the object is mx, which is moving with 5v speed, and then the Y is at rest. It's not moving at all. So, and then after they're colliding, the object X come and collide with object Y, and then they are moving together with the velocity v. Okay, they are sticking together after collision. So the block X moving with speed 5v collides head-on with a stationary block Y of mass my. The two blocks stick together and then move with common speed v, as shown in figure 3.2. Use the conservation of momentum to show that the ratio mx to my is equal to 4. So there is a collision. It's a collision. In every collision, we know that the momentum will be conserved. So according to conservation of momentum, what can you write? Momentum before collision is equal to momentum after collision. So it's actually net momentum, after collision. So the momentum before collision is how much? The momentum of X plus momentum of Y. So let's say the mass is mx and then velocity is 5v. So the momentum is mass times velocity. So mx times 5v. That's the momentum of the first object, and the second object has no momentum at all, so you can write plus 0 or ignore, that doesn't really matter. So mx times 5v is the net moment before collision. That should be equal to net momentum after collision. So what is the net momentum after collision? The total mass times total velocity. So the total mass is mx plus my. That's the total mass because they are sticking together and then they are moving with the velocity v, right? So you can do the math to show the required thing. What is that? My over mx is 4. You can show that by calculations. So let me do that. 5v times mx is equal to mx plus my times v. So the v on both sides cancel. Mx plus my divided by mx is equal to 5. So 1 plus my over mx is equal to 5, which gives that my over mx is equal to 5 minus 1, 4. So this is a required thing to show, right? And then let's move to the next part. Calculate the ratio, the total kinetic energy of x and y after collision to the total kinetic energy of x and y before collision. Okay, so the total kinetic energy of x and y after collision. So after collision is this one. So they are moving, they are sticking together. The total mass will be mx plus my, and then they are moving with the velocity v, which means the numerator, the total kinetic energy of x and y after collision will be half total mass, which is mx plus my v squared. So they are moving with the velocity v, that's why it will be v, because the kinetic energy is half mv squared, right? So divided by half the total kinetic energy of x and y before collision. So before collision they are separate, so you need to talk about kinetic energy of the x plus kinetic energy of y. But kinetic energy of y is obviously 0 because it's not moving at all, it's stationary. So the kinetic energy of x is only the total kinetic energy of x and y before collision. So that is equal to half times mass is mx, the velocity of the x is 5v, so 5v squared. If you write 5v squared, that will be wrong, guys, because the velocity should be squared, like 5v whole squared. There is a lot of difference, 5v squared and 5v whole squared. Okay, so let me write it. So half but from this equation, what can you write? My can be written as 4 times mx. Yes or no? 4 my is equal to 4 times mx. So what I'm doing, I'm replacing this my with 4mx. Okay, so mx plus 4mx. You must take note of it because my is replaced with 4mx from this equation. Okay, and then times v squared divided by half mx, 5v squared, 5v whole squared, which is 25v squared. Remember, guys. Okay, so the v squared cancel, half cancel, and then in the numerator what is left? 5mx, because mx plus 4mx is equal to 5mx divided by mx, 25 mx, because the 25, you should not forget this 25, right? So 25 mx. So mx cancel, 5 ones are 5, 5s are cancel, so 1 over 5, which is equal to 0.2. So the ratio expressed in the decimals. Okay, the ratio is expressed in the decimals. Okay, 0.2. Let's move the next part of the question, which is third part of B. State the value of a ratio in II for a perfectly elastic collision. So what is a perfectly elastic collision? A collision where momentum is conserved and also kinetic energy is conserved, right? So if the kinetic energy is conserved, that means the total momentum before collision will be equal to total momentum after collision. So let's say the total momentum before collision, the total kinetic energy before collision is 100 joules, example, and then that should be same kinetic energy after collision also. So if you find the ratio of 100 to 100, that will definitely be 1. Okay, that will be 1. So just 1 will give you 1 mark. You don't need to explain everything, okay, because when it is a 1 mark question, mostly that is a direct answer. Yeah, remember that. And then let's move on to the C part. The variation with the time t of the momentum of block X in B is shown in figure 3.3. So this is the momentum. The block is momentum of X, yeah, block X only. See here, constant momentum decreased at constant rate. Okay, the gradient is constant, so the rate of change in momentum is constant, and then again constant momentum. So what do you understand from this? From t is equal to 0 to t is equal to 20 millisecond, what's happening to the force? Like describe qualitatively the magnitude and direction of the resultant force, if any, acting on block X in the time interval t is equal to 0 to t is equal to 20 milliseconds. Of course, there is no change in momentum, there is no force. You can say that no force, or you can say zero force, no force. You can say zero force also, no problem. So time t is equal to 20 milliseconds to time t is equal to 40 milliseconds. So what's happening from 20, this is a 20, and then 20 in millisecond, remember guys, this is a millisecond. So 20 milliseconds to the 40 milliseconds, what's happening? The momentum is falling constantly. The momentum is falling constantly means constant force is acting. Constant force is acting. So because what is the formula for the force? Force is equal to rate of change of momentum, so delta p over delta t. So you can see this delta p is on y-axis and then delta t is on the x-axis. So basically you can say the gradient of the momentum time graph is force. Since the gradient is constant, the force should also be constant. But at the same time, what you must understand, the momentum at the start was so much of the block X, and then what happened after collision? Momentum fell, like momentum reduced, which means that the force should act against the motion, right? It's just like a car moving with certain velocity and then applied brakes, and then after some time the velocity decreased. What's happening there? So there is a resistive force on the car, right? That's why the momentum the velocity decreased and then momentum also decreased. So here you can say that constant force. Okay, there is a constant force, but you need to tell the direction also. It's not enough to say the constant force, you need to tell the direction also, which is opposite to the motion. Opposite to the motion. Opposite to the motion, right? So on figure 3.3, sketch the variation of the momentum of block Y with time t from t is equal to 0 to t is equal to 60 milliseconds. Now it's kind of important and then tricky. On the same graph, you must draw the momentum of block Y. Let's see here. From the 20 until the 20 milliseconds, the block Y has no velocity, which means it has zero momentum. So the line should pass from from the origin until there, 20 milliseconds on the x-axis. After that, it is being collided. But what happened? The velocity 5v, velocity 0, initially 0. After collision, the velocity went to v. Velocity went to v. Right. So momentum of the block Y with you have to talk about the block momentum Y. And then there's the velocity v, but velocity v, and the mass is already 4 times than the x. Let's say this should be 4 times of the momentum of the 4 times mx, you can say mx, you can say. So if the momentum of the first block is 5vx, and then the momentum of y after collision will be 4xv. So basically it is moving with v only, but the mass of the y is huge, like 4 times of the mass of x. Okay, that's why the graph until 20 milliseconds, so it will be 4 points, because 1 box, 2 box, 3 box, and then 4 box, and then the momentum of the y increase in this duration. After that it will be going straight line, right? So the momentum of the y is increased after collision. It's quite clear from the question. Before there was no momentum of y, after the collision there is certain momentum, so basically the momentum has increased. That's what you must understand, and then that should be reflected on the graph. So on the graph the momentum of y is increased, at the same time momentum of x is decreased. Okay, how can you check whether your answer is right or wrong? From the graph itself you can check. Actually this is extra information that I am giving. You see here, the total momentum before collision is momentum of x and momentum of y, which is equal to 5 square boxes. Okay, 5 boxes. First box, second box, third box, fourth box, fifth box, 5 boxes. Anything, it can be any unit, like 1 kg meter per second, you can assume, no problem, because they did not calibrate the axis. Now momentum after collision, this is the momentum of x, this is the momentum of y. So what is the momentum of x? 1 unit, right? And then what is the momentum of y? 4 units. So 1 plus 4 is what? 5. So basically before collision momentum is 5 units, after collision also momentum is 5 units. So this is the question number 3.